Welcome to the 5th day class of the metal cutting and machining process. In this classes we have compiled all the metal cutting relations. We are solving the problem by using the metal cutting relations like chip thickness ratio and chip reduction coefficient, rake angle, shear angle and shear strain, cutting force, shear force, friction force and normal to the friction force, coefficient of friction. We have solved all those problems and we have discussed the theoretical part of the shaping, planning, slotting and turning. We have to use the drilling machine, types of drilling machines and millings, the difference between up milling and down milling, grinding wheel nomenclature and the gear manufacturing process. So this is the fifth day we are in this fifth day we are going to concentrate on unconventional machining and the remaining topics. So students practice all those problems in an effective way and it will be more useful for the GATE exams and as well as engineering service exams and any competitive exams such as ISRO, RRB like that, and if you practice these questions it will be useful for your placement also. So we will proceed with the 5th day class. To increase the MRR in electrochemical machining, what are the favorable factors? So I want to increase this variable. So my numerator will increase, atomic weight will increase and current supplied is increased. So when you increase atomic weight and current supplied, the MRR will get increased. Otherwise we can reduce the valency. This V is the valency, but Faraday constant is constant, or we can reduce the density. So these are the four possibilities to increase the MRR. These are the four possibilities to increase the MRR in electrochemical machining. As an engineer, we always need the selection process. We should make the decision whenever there is a variety. So here we are choosing the electrolyte for the electrochemical machining. So when we choose the electrolyte for the electrochemical machining, we should remember these 2 points. This electrolyte should not allow the dissolution of cathode material. And second thing, it should have high electrical conductivity. This electrolyte has a high electrical conductivity. These are the 2 things we have to remember for the selection of electrolyte. In ECM, there are 2 electrolytes. One is passivating electrolyte and another one is non-passivating electrolyte. So we are having 2 types of electrolyte, passivating electrolyte and non-passivating electrolyte. So this passivating electrolyte is used for stock removal process. So it can be used for stock removal process. This non-passivating electrolyte is used for finishing purpose. In ECM process, the material removal rate occurs due to the following action. It is because of the ion displacement of the in the electrolyte. So because of this thing, the material is removed. So it works on the principle of ion displacement. When the ions are moving, the material is removed. Now we are going to discuss the metal removal rate of different unconventional machining process. So what are the process? It is a LBM, laser beam machining, has the low MRR. It is 5 millimeter cube per minute. The electron beam machining has 10 millimeter cube per minute. So compared to LBM, EBM is somewhat higher. And USM, ultrasonic machining, removes 180 millimeter cube per minute. And EDM has higher MRR, 5000. So it has increased 10 times. So it is 30 times nearly compared to the previous USM, 5000 millimeter cube per minute. And ECM, it is somewhat much more higher, 10,000 millimeter cube per minute. Now we are going to know about the formula. MRR in ECM is Zi by Vf rho, where Z is the atomic weight, I is the current carried, V is the valency, F is the Faraday constant and rho density. So when it is an alloy, for example, if it contain A, B and C, it is alloy of 3 compounds. So it may be 0.18, 0.5 and 0.32. So different compositions are given. The alloy is made by different composition and percentage will be given. So we have to find out the V by Z equivalent. Instead of using this formula, we have to use I by V by Z equivalent F into rho. So V by Z equivalent can be calculated by V1 Z1 X1, V2 plus V2 is divided by Z2 X2 plus V3 by Z3 X3, where X1 and X2 X3 are percentage of composition. X1, X2, X3 are percentage of composition, and V and Z are the corresponding valency and corresponding atomic weight. So we have to calculate the equivalent this term, and we have to substitute in the formula 2. So in this way we can find out the MRR of the alloy. When we machine the alloy in ECM, we have to use this formula. When it is single element, we can use this formula. Yes, we are going to discuss about some of the basics of metal cutting and machine tools. What do you mean by machining? Machining is the removing unwanted material from the workpiece. So we are having some workpiece is raw material is there. So we want to cut these portions. So we want to make like this. So we want to remove this material. So it is called as, it can be done by machining operations. So the removed material are termed as chips. So metal removal process is broadly classified into 2 types. One is conventional and another one is unconventional. In conventional, we are having cutting operations and abrasive types. So in cutting, we can axisymmetric cutting or prismatic cutting. Axisymmetric cutting as boring, drilling, tanning or axisymmetric cutting. Prismatic cutting, milling, shawing, shaping. Those are all prismatic cutting. In abrasive, we are having bonded cutting and loose cutting. In bonded cutting, we are having grinding, awning, super finishing are all come under the bonded cutting. Loose cutting, it is a lapping. In lapping, we are using loose dust type abrasives. We are going to discuss about the metal cutting operations. Metal cutting process are broadly classified into, it is orthogonal cutting process and oblique cutting process. This orthogonal cutting process can be called as 2-dimensional cutting, and oblique cutting is called as 3-dimensional cutting. In orthogonal cutting, it is oriented 90 degree to the tool feed direction. We are having 90 degree to the tool feed direction. In oblique cutting, it is oriented at an acute angle to the tool feed. So this is the, you can see the diagram. Here the cutting edge is 90 degree, here the cutting edge is 60 degree. So you can see the feed direction. So this is the feed direction. For the feed direction it is 60 degree, for the feed direction it is 90 degree. So it is a knife edge, and here the edge is inclined. So that surface is the rake surface, rake face. So this is the rake face and this one is the rake face. So we can easily observe the orthogonal cutting and oblique cutting. Next thing we are going to discuss is the difference between orthogonal cutting and oblique cutting. The orthogonal cutting is the 2-dimensional cutting and oblique cutting is the 3-dimensional cutting. Only one cutting edge in action in orthogonal cutting. In oblique cutting, more than one cutting edge come into the action. Here cutting edge is normal to the direction of tool feed. There cutting edge is inclined at an angle to the direction of the normal feed, tool feed. Here width of the cutting edge is more than the width of the work being machined. So here the width of cutting edge is not more. In oblique cutting, the width of cutting edge is not more than the width of the work being cut. The direction of chip flow velocity is normal to the cutting edge of the tool. Here direction of chip flow velocity is at an angle with the normal. So this is it is a two mutual perpendicular force components are acting. Here 3 component of force is acting. In orthogonal cutting, surface finish is poor. Here surface finish is good. In oblique cutting, surface finish is good. And in orthogonal cutting, tool life is less. In oblique cutting, tool life is more. And the chip get coiled in the spiral direction. Here chip flow in the sideway direction. In orthogonal cutting, chip get coiled in the spiral fashion. Here chip flow in the sideway direction. In orthogonal cutting, chip flow angle is 0. In oblique cutting, chip flow angle is more than 0. Now we are going to know about the here cutting force are acting in x and z direction. Here cutting force act in x, y and z direction. Here maximum chip thickness may always occur at the middle. Here maximum chip thickness may not occur at the middle in oblique cutting. Tool may generate the surface parallel to the work face. The tool may or may not generate surface parallel to the work face. So this is a beautiful classification of types of chips and conditions where different types of chips are formed. So here continuous chips is there, the next one is continuous chips with built-up edge is there, and third one is discontinuous chips. Continuous chips is produced in ductile workpiece. Continuous chips with built-up edge is also produced in ductile material, but discontinuous chips is produced in the brittle material. So here the cutting speed is I, here the cutting speed is I, cutting speed is I, built-up edge because occur at the low speed, and for brittle material discontinuous chips also at the low speed, and in continuous chips the feed is low, the feed is low, with the built-up edge the feed is high, and for discontinuous chips also the feed is high. So we are having low depth of cut. In continuous chips what we are having, it has low depth of cut only produce the continuous chips. When the depth of cut is high, so built-up edge will be formed in the ductile material, and here also high depth of cut. So here rake angle is high. In rake angle is an angle which helpful for cutting. So high rake angle continuous chips. Here low rake angle, here also low rake angle. You can observe that. The continuous chips produced by the sharp cutting edge, whereas the built-up edge, when the built-up edge is formed due to the dull cutting edge. And there are efficient cutting fluid or sufficient cutting fluid. Here insufficient cutting fluid. The continuous chips is produced because of the low friction in the chip tool interface. This is a tool and this one is a chip. This interface is called as chip tool interface. So you can observe the chip, there it is continuous, and this is a segmental chips or discontinuous chips. So you can see the built-up edge, it is marked in black. So this is the built-up edge. Because of the built-up edge, so the tool may get broke also. So these are the major classification for the difference between continuous chips, discontinuous chips and continuous chips with built-up edge. So next thing we are going to discuss is heat distribution in metal cutting. So what is the amount of heat taken by each and every one? So we are having chips here, we are having chips. So chips take 80% and work take 10% and another tool take another 10%. So this is the common thing, and we are having 3 different zones. Primary deformation zone, in that heat generation due to the plastic deformation, and the secondary deformation zone, there it is due to the drag between the chip and rack face, and the work tool contact zone, there it is produced to the burnishing action. So in the primary deformation zone it is due to the plastic deformation, in the secondary deformation zone it is due to the drag, and the work and tool contact zone it is due to the burnishing. So based on the tool geometry, the tools are broadly classified into A cutting tool has one or more sharp cutting edges. So cutting tool means it should have the cutting edges. It should have the cutting edges. Cutting tool means it should have the cutting edges. So the cutting edges can be classified as the tools are classified as single point cutting tool and multi-point cutting tool. A single point cutting tool has only one cutting edge. Multi-point cutting tool has many cutting edge. So this is the terminology for the cutting tool. You can observe the diagram. As a mechanical engineer or production engineer or industrial engineer or metallurgical engineer, you should know the dimensions or terminology of the single point cutting tool. In the single point cutting tool, the portion without cutting edge is called as shank. The portion with cutting edge has different face. This face is called as rake face. This face is called as rake face, and so this one is the rake face. And the second thing is, here the sharpness is the cutting edge. So and this one is the back rake angle. So we are observing the back rake angle. So it is an arrow. Between these two arrows we are having back rake angle. And at the end of the tip we are having nose radius. So the side one on the transverse surface we are having the side flank. This one is the end flank, and we are having the side flank is a deviate at an angle is called a side cutting edge angle. End flank is deviate at an angle is called as end cutting edge angle. And we are having end relief angle. This is the end relief angle, and this one is the side relief angle. So we are having back rake angle, side rake angle, end clearance angle, side clearance angle, end cutting edge angle, side cutting edge angle, nose radius. So these are 7 terminology which is significant in the nomenclature. So you should observe the diagram clearly and draw 1 or 2 times. You have to practice this diagram and remember all the things. This is the very important point of the interview point of view. In all the competitive exam, this question may be repeatedly asked. So it is a question prone zone. So you have to observe, you should take care of these things. So we are having different views of the single point cutting tool. I had gone to DRDO interview. In that the first question, are you a production engineer? So please draw the single point cutting tool. So you can observe here, this is the shank, this is the non-cutting portion, and this one is the nose radius. Parallel to the shank, this is the face, and we are having the end cutting edge angle, here side cutting angle. So that is the top view. So we are having top view and front view and side view. Okay, so we are having face, shank, side cutting angle and end cutting angle. So coming to this point, so it is the angle between face and flank. This is flank and this one is the face. Angle between face and flank is called as lip angle. So this is the base and this one is the side view, top view and front view. So we are having end relief angle here and back rake angle here. Okay, end relief angle, back rake angle, and here we are having side rake angle and the side relief angle. So in the side view we have get the side rake angle and the side relief angle. So based on that we can observe this diagram. You have to repeatedly practice and get the image. Get the image and it has to be focused in the mind. It has to be focused in the mind clearly. So we are having how many terms are there? Shank you can easily remember, base you can easily remember, but here 2 angles. It is back rake angle, end relief angle, side rake angle, side relief angle. Here end cutting edge angle, side cutting edge angle, and nose radius. So here 3 parameters. Here 3 parameters are coming, and here 2 parameters are coming. Here 3 parameters are coming. 3 angles you should know. So totally 8 things we have to remember in this diagram. So make a note of that. So rake angle. How will you define the rake angle? Rake angle is angle where whenever you are defining the angle, it has to define in between two face. So it is between the face of the tool and the rake face. It is the face of the tool and the rake face. So it is the rake face, the normal to the cutting direction. So we are having three types of rake angle. One is negative rake angle, positive rake angle, and zero rake angle. So this negative rake angle is always preferable in carbide tipped tools. Negative rake angle preferable in carbide tipped tools. It is stronger in compression. The positive rake angle, it is stronger in shearing and bending. Okay. And back rake angle, how the back rake angle are described? It is an angle between the line. This is the back rake angle. It is an angle between the line parallel to the tool axis. So we can draw the tool axis. So angle between the line parallel to the tool axis. This is the line parallel to the tool axis through the tip. So it is passed through the tip. Angle between it passed through the tip. So axis passing through the tip. Line parallel passing through the tip. And the rake face. So this is the rake face. So this one is the rake face. So that is the angle. Okay. Angle between the line parallel to the axis passing through the tip and to the top face, which is angle is measured in a plane perpendicular to the base. Angle is measured. So we can say that the angle is measured to the perpendicular to the base. So we are having the diagram for tool life and back rake. We have to focus this diagram. We have to focus this diagram. It is the tool life and back rake angle. So tool life and back rake. What happened? When the back rake angle increases up to certain time, the tool life is increases. After that, it goes on decreases. So the material and back rake angle, the soft and ductile material. We are having soft and ductile material. You should go for positive rake angle. When we have hard and brittle material, we can go for negative rake angle. For hard material, brittle material, they always go for negative rake angle. And brass is the famous thing. For brass, zero rake angle. Single point cutting tool ideally have positive rake angle. The rake angle means cutting. The rake angle means perfect cutting, and the strength of the cutting tool depends on the rake angle. Strength of the cutting tool depends on the rake angle. So the next after back rake angle, we are going for side rake angle. The side rake angle, you can observe the previous diagram. The side rake angle is the angle between the rake face and line passing through the tip to the perpendicular to the tool axis. Angle is measured in a plane perpendicular to the base. Normally this angle varies from 5 to 15 degree. Normally this angle varies from 5 to 15 degree. Large positive side rake angle result in less chip formation and less cutting force, good surface finish and low heat dissipation rate. So when the side rake angle is more, what happen? It is chip formation is less and cutting force is less and heat dissipation is less. So three things are less to produce a good surface finish. Next we are going to discuss is side relief angle or clearance angle. Relief angle also called as clearance angle. Relief angle also called as clearance angle. Side relief or end relief, side clearance or end clearance. So this relief angle, the purpose of relief angle, why the clearance is given? The clearance is given to increase the tool life. That means it reducing the chance of tool breakage. We are safeguarding the tool. Safety is our first priority. As an engineer, we should make that safety is our first priority. Clearance angle is an angle defined as between the machined surface and underside of the tool. That means called flank face. It is the angle between the machined surface and flank face. If relief angle is too large, so it has to be given as minimum. If relief angle is too large, what happens? The tool may break the chip. The tool may break the chip. So relief angle is too large means tool may break the chips. So in other cases, if the angle is too small, the tool will rub the workpiece. The tool will rub the workpiece. Small means rubbing take place and more heat will be produced. When there is rubbing, what happens? Heat will be, when you rub the hand, what happens? The heat will be produced. So when the clearance angle is small, more heat will be generated. When the clearance angle is large, tool may break the chip. Tool may break the chip. For machining hard material, so when the material is hard, the relief angle should be small. For machining softer material, the relief angle should be large. So soft material, relief angle or clearance angle, alpha clearance will be large. Hard material, clearance angle will be, so it is vice versa. So hard it will be less, soft it will be large. A smaller angle should be used for heavy feed. Similarly, for feed is more, we can go for smaller angle. For feed is less, we can go for higher angle. So this larger angle is for finishing cut. So feed is less means you should remember it is finishing. Feed is more means it is roughing. For roughing, the clearance angle will be less. For finishing, the clearance angle will be more. So these are the important points while machining the component. Next we are going to see side relief angle. The side relief angle is the side flank. The side relief angle is the angle between the side flank and the line passing through the tip of the perpendicular to the base. So it varies from the 5 to 15 degree. This angle is provided to avoid soft rubbing due to elastic recovery. It is provided to avoid side rubbing due to elastic recovery. When the workpiece is compressed, it has some elastic deformation. That elastic recovery, because of elastic recovery, side rubbing take place. So to avoid side rubbing, we are providing side relief angle. We are providing side relief angle to avoid side rubbing. And next is end cutting edge angle. Why this end cutting edge angle is provided? This is the angle between the end cutting edge and line passing through the tip of perpendicular to the tool axis. Line passing through the tip perpendicular axis. Line passing through the tip perpendicular to the tool axis. The angle is measured in the plane parallel to the base. Due to the small end cutting edge angle, tool may chatter. When the end cutting edge angle is smaller, so chatter. When end cutting edge angle is smaller, there the problem chatter. Chatter means vibration. It will vibrate. And the normal value of end cutting edge angle is 8 to 15 degree. End cutting edge angle 8 to 15 degree. So you can easily remember the 8. 8 is the famous number for license. So end cutting edge angle 8 to 15. Next term we are going to see is end relief angle. It is angle between the end flank. It is angle between the end flank and line passing through the tip perpendicular to the base. Line passing through the plane tip perpendicular to the base. In ductile material, this elastic recovery is more. Ductile material, elastic recovery is more. So large clearance angle. For ductile material, large clearance angle. Next we are going to see about the side cutting edge angle. Side cutting edge angle is the angle between the side cutting edge, and line extending the shank. When you extend the shank, measure in the plane parallel to the base. You have to measure in the plane parallel to the base. Feed represent the uncut chip thickness, depth of cut represent the width of the chip. So always depth of cut you can equate to width of the chip, and feed represent the uncut chip thickness. So feed represent the uncut chip thickness, and depth of cut represent the width of the chip. So it can be used in some of the problematic point of view. So we are having the diagram for tool life and side cutting edge angle. So this is the cutting edge. In the cutting edge you can have the parameters. It is a W and a psi D. So W can be calculated by D by psi. So this is the W. W is the hypotenuse. So hypotenuse, so cos adjacent by hypotenuse. This is the adjacent angle D. So D by W equal to cos psi. D by W equal to cos psi. So the psi is the cutting edge angle. So Ft by F equal to cos psi, and true feed Ft equal to F cos psi. So when you want to calculate the true feed equal to F cos psi. So it is a simple triangle diagram, so you have to remember. So which W is the hypotenuse, so W equal to D by cos psi. So here Ft true feed equal to F times of cos psi. So that is the thing you should remember. By observing the diagram, it is a simple thing you can easily remember. Always this Ft is equal to F uncut chip thickness and nose radius. So nose radius is, it provides the good surface finish, because you can remember the formula H equal to, H equal to F square by 8R. When you have higher nose radius, the height of unevenness is less, that means surface finish good. So higher nose radius, higher good surface finish. So nose radius, it provide good surface finish. Not only that, longer tool life will be longer. So because a sharp point at the end of the tool is highly stressed, when the point is sharp, it is highly stressed and short-lived and leaves a groove on the finished workpiece. So it may have grooves. So large nose radius, when the nose radius is large, what is the disadvantage? So will result in more power consumption. Large nose radius produce it significance into more power consumption and better heat dissipation, because the contact area is more, better heat dissipation and higher tool life. These are the significant points for the nose radius. For the nose radius, we have to remember these points. So we are having lead angle. Lead angle is the angle determined by the tool holder which must be chosen for particular job. Angle decided by the tool holder for the particular job is called as lead angle. So positive lead angle has the two functions. It produces the thin chips. Positive lead angle produce the thin chip and protect the insert. So when we have the insert, like this, so we are facing the two material like this, so it protect the insert. So when we have the positive lead angle is positive, means it protect the insert. So it protect the insert. So this is the insert This is the holder, this one is the holder, so it protect the insert. So when the lead angle is positive, it protect the insert. So next we are going to discuss about the tool signature. We are going to discuss about the tool signature. What do you mean by tool signature? So this is the American standard system. We are having first term back rake angle, and we are having back rake angle, side rake angle, end flank angle. This flank angle also called as end relief angle, okay, or end clearance angle. Side flank angle, side relief angle, side clearance angle. So three names are there, okay. And it may be, as per the American standard system, always back rake angle come first. So back rake angle, after that it is side rake angle, after that it is end clearance angle, next side clearance angle, then end cutting edge angle, then side cutting edge angle, then nose radius. So these are the 7 terminology used to describe the American standard association system for the tool signature. Next is orthogonal rake system. Orthogonal rake system is nothing but it is also consisted of 7 terms. The first term is inclination angle or angle of inclination. Next normal rake angle or orthogonal rake angle. Next principal flank angle, axillary flank angle, axillary cutting edge angle, principal cutting edge angle, and nose radius. These are 7 terms you should remember. So inclination angle, you have to form the mnemonic code IOP, inclination angle, orthogonal rake angle, principal flank angle or principal clearance angle. So axillary flank angle, axillary cutting edge angle, principal cutting edge angle, and nose radius. Okay, IOP, AAP, nose radius. So this is inclination angle, this is orthogonal rake angle, principal flank angle, axillary flank angle. So here also flank, here also flank. So this one, these two are cutting edge angle. Okay, so inclination angle, orthogonal rake angle, principal flank angle, axillary flank angle, axillary cutting edge angle, principal cutting edge angle, nose radius. So always for remembering, make some mnemonic codes. So we are having sharp tool and curved tool. For peak to valley height can be calculated by using these two formula. This is for the first formula is for nose radius. We are having the f square by 8 or h max equal to another formula, h max equal to f by tan psi plus cot psi 1, and the center line average equal to h max by 4. In some question, center line average will be asked. This is the maximum peak to valley height, and center line average CLA. Center line average means you can get the surface finish. So CLA, what is the CLA value? They will ask what is the center line average value, CLA value, that is equal to h max by 4. It is a quarter of the h max. So for h max we are having two things. One is the tool with nose radius, tool where nose radius effect can be neglected. So for that this formula can be used. This is the relationship between the angles. So tan alpha equal to tan alpha s sin alpha tan alpha b cos lambda. So you should have the relations. By using these relations we can solve the problem. You should make a note of this, all the 4 formula. If this question asked in the IES. So the relationship between the angles. So alpha b is the back rake angle, alpha is the side rake angle, and lambda is the principal cutting edge angle, and the relationship between the lead angle and side cutting edge angle. This is the psi s is the side cutting edge angle. Psi s is the side cutting edge angle. The lambda is the lead angle. Lambda is the lead angle. So alpha b is the back rake angle. Alpha s is the side rake angle. In the tanning process, mechanism of tanning process, the T1 equal to f cos psi, omega equal to d by cos psi s. So this cos psi s is nothing but side cutting edge angle. So to calculate T, uncut chip thickness, we have to use F times of cos psi s. For W, D by cos psi s. Okay. Next, it is an important calculation, cutting speed calculation. Cutting speed is V equal to pi dn, where D is the diameter and n is the number of revolution, and the depth of cut can be noted as D, and uncut chip thickness noted as T1, F is noted as feed. So here the important man, merchant is coming. Merchant, always as an engineer we have to assume we made some assumption. Why? Because assumption converts the complex problem into simple problem. For the simple problem only we can get the solution. For complex problem, the solution, the process of making solution will be more. So merchant made some these assumptions. What are the assumptions? The tool is perfectly sharp and no contact along clearance face. No contact along clearance face. The surface where shear is occurring in a plane. So there may be some shear plane is there. The cutting edge is straight line. The cutting edge is straight line and extending perpendicular to the direction of motion, and generate the plane surface on the work. And the next thing is the chip does not flow on the to either side. No side flow, no side spread. Chip won't flow on side. The uncut chip thickness is always constant. The uncut chip thickness is always constant. In real time it may vary, but merchant made the assumption uncut chip thickness is always constant. And the width moves with the uniform velocity. And here the merchant assumed that continuous chip is produced without the built-up edge. Continuous chip is produced without the built-up edge. And works moves with the uniform velocity. And stresses on the shear plane are uniformly distributed. The stresses on the shear plane are uniformly distributed. So these are the assumptions made by the merchant to draw the merchant circle. So what are the forces that merchant has to taken into consideration? So he take the thrust force. So we are having the cutting force. We are having the cutting force and the thrust force. So he takes a resultant force. So with the help of this cutting force, thrust force and resultant force, by using this triangle he makes a resultant as diameter, he construct a circle. That circle can be called as merchant 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 circle. So he used this resultant as diameter, and the cutting force triangle he calculate the merchant circle. And we are having the shear force. We are having the shear force and normal to the shear force. So those two form another triangle. And the next triangle is we are having friction force and normal to the friction force. So there are 6 set of forces are there. There are 6 set of forces are there. All the 6 set of forces inside the Mohr circle. Inside the Mohr circle. So now we are going to draw the Mohr circle. You can easily remember. Now you are going to draw the Mohr circle. You can easily remember. So this is the cutting force, and this one is the thrust force. So we are having the resultant force. So this resultant force, by using this thing, he has to construct the circle. That circle is called as merchant circle. That circle is called as merchant circle. This circle is called as merchant circle, and this merchant circle we have to get the shear plane. So shear plane, it is at an angle of pi from here. Okay, so we have to connect with the resultant force. This one is the normal to the shear force. This one is the shear force, and this one is the normal to the shear force. So it will make another triangle. Next thing is, so we are having the normal line here, and our tool will be like this. It will contact at this point. So we are projecting this line, like this line and meet it here. That is the friction force, and this is the normal to the friction force. So this is the merchant circle. So all the six forces come inside the merchant circle. So by solving by using the simple triangle method, we can get the Fs equal to Fc cos phi, Ft sin phi. Fn equal to Fc sin phi plus Ft cos phi. So among these two forces, which force is larger? And so you should remember that. So here you can see that Fs is smaller. So Fs is smaller than that of Fn. So that is the thing. And similarly, the here friction force N is smaller than that of F. So whenever larger force, the plus will come. See here, larger force plus will come. Here Fn is larger plus, and the smaller force negative will come. And always you have to remember that whenever Fc is coming for subtraction, Fc is coupled with cos phi. Here Fc is coupled with cos alpha. For subtraction, the cutting force is associated with cos term. So these two things you have to remember, and you have to find out the coefficient of friction. The coefficient of friction equal to tan beta. That is equal to F by N. You are simply substituting those formulas here. Ft plus Fc tan alpha, Fc minus Ft tan alpha. So for subtraction, Fc will come under the front. For addition, Ft will come under the front. So Ft plus Fc is tan alpha divided by Fc minus Ft tan alpha. So area of shear plane can be calculated by area of shear plane W into T by sin pi. W is the width of the cut. So these four formulas, by using these five formulas, so 1, 2, 3, 4, these five formulas, all these five formulas are important for the competitive exam point of view. All the five formulas are important for the competitive examination point of view. So here the shear force can be calculated by shear stress into that area, shear area. Shear area is Wt by sin pi. So force, stress into area gives force. Stress into area gives force. Stress is tau, that is shear stress, and area is Wt by sin pi. So we can get easily. And normal, for normal stress, it is sigma into As. So sigma Wt by sin phi. So area is same for both the things. It is same area. Mean normal stress we can be calculated, and it can be related with the resultant also. Fs equal to R cos theta plus beta minus alpha, or pi plus beta minus alpha. That is not theta, it is pi. Pi is the shear angle. So here you can make the small correction. It is pi. Okay. So in that way we can solve n number of problems by using this formula. So these formulas are very, very significant. So you have to focus, you have to make a note of this formula. You can solve whatever may be the problem which is coming, you can easily solve the problem. So how the relation can be obtained? So what is the condition for, merchant condition for minimum energy condition, merchant minimum energy principle. So he is differentiating the term to find the minimum. So this is the minimum. So from this only 2 pi equal to 2 pi plus beta minus alpha equal to pi by 2. So here it is 2 pi plus beta minus alpha equal to 5 by 2. So therefore phi equal to pi by 4, here the term is wrong, 5 by 4 plus alpha by 2 minus beta by 2. Okay, 5 by 4 plus alpha by 2 minus beta by 2. So this is the thing you should remember. It is a merchant relation. You have to remember 2 pi plus beta minus alpha equal to pi by 2, where pi is the shear angle, beta is the friction angle, alpha is the rake angle. Next is chip thickness ratio. Chip thickness ratio can be defined as the T1 by T2. T1 is the uncut chip thickness and T2 is the chip thickness. So you can get tan pi equal to R sin alpha divided by 1 minus R sin alpha cos alpha. Tan equal to R cos alpha. Here you have to make a small correction. This is not R sin alpha. This is R cos alpha divided by 1 minus R sin alpha. Or we can say that R equal to sin pi by cos pi minus alpha. You can use this formula also, R equal to sin pi by cos pi minus alpha. So we can get the relation tan pi equal to R cos alpha divided by 1 minus R sin alpha, or R equal to sin pi by cos pi minus alpha, R equal to sin pi by cos pi minus alpha. So by using this formula we can solve the problems. We are having for R, we are having another formula, R equal to T by Tc, that is Vf by Vc. Here we can use that. It is not that V by Vf. Our formula is Vc by V. This is the velocity of chip to the top velocity, cutting velocity. This is cutting velocity. So cutting velocity is larger. So sin pi by cos pi minus alpha, that is equal to Lc by L. When alpha equal to 0, what happens? R equal to tan pi. It is an important condition we have to remember. When alpha equal to 0, R equal to tan pi. And the chip reduction coefficient is the inverse of the chip thickness ratio. Chip reduction coefficient is the inverse of the chip thickness ratio. Chip reduction coefficient is the inverse of the chip thickness ratio. And the calculation of shear angle, pi equal to tan inverse of R cos alpha divided by 1 minus R sin alpha. Because we know that tan pi equal to R cos alpha divided by 1 minus R sin alpha. So here we are having the formula. So we can say that when the metal is cut, there is no change in volume. It is important assumptions. So before cutting, with after cutting are equal. So with after cutting and before cutting are equal. So we can say that. So T1 by T2 equal to L1 by L2. This is L2 by L2. It is inverse. So T1 by T2 equal to L2 by L1. So we can get that formula tan pi equal to R cos alpha divided by 1 minus R sin alpha. So that is the formula we are getting. So whenever there is we want to calculate resultant force. Resultant force is the sum of the square of the cutting force, sum of the square of the cutting force and square of the thrust force. This horizontal force is the cutting force and vertical force is the thrust force. So we have to use that formula. When you square, you can get the resultant force. So we should know how to calculate the power. The power is nothing but force. The product of force and velocity is power. So when you multiply the cutting force with the cutting velocity, it is called as cutting power. When you multiply the shear force with the shear velocity, is the shear power. When you multiply friction force and with the velocity of chip, it is the friction power. So you can find out the three types of power in the metal cutting operations. So this one is the friction power, and this one is the cutting power, and this one is the shear power. The product of force into velocity can be called as power. So the total power is equal to sum of the shear power and the friction power. So the total work done is the shear work and so this is the cutting. So we can calculate it. So what is the percentage contribution in loss? What is the percentage of shear to the total? So you can, this is the percentage content. So you can easily, this is the question asked in the gate exam. So here you can see the cutting force triangle. This triangle is the cutting force triangle. The cutting force triangle and the shear force triangle. Two triangles are there. This is the cutting force triangle, and this triangle is the shear force triangle. So both are related, and both are related to calculate these two forces. Both are related to calculate these two forces. So shear force is smaller, so negative will come. So Fc cos phi minus Ft sin phi is the value, and for normal force it is positive. Fc sin phi plus Ft cos phi. So this is the Western circle we have drawn it earlier. So you can see all the three triangles. It is a cutting force triangle. For example, we can name it. You can remember it. This is OAB. OAB is the cutting force triangle, and OCB is the shear force triangle, and OBD is the frictional force triangle. So all these three triangles are inside the merchant circle. So that we can calculate those forces are interrelated. So now we are having the coefficient of friction. Coefficient of friction is the tangent of the friction angle, or it is the ratio of frictional force to the top normal reaction. The ratio of frictional force to the top normal reaction is termed as coefficient of friction, or we can substitute the value of frictional force and normal force here in terms of thrust force and cutting force. We can get this formula: tan theta equal to Ft by Fc plus tan alpha 1 minus Ft by Fc tan alpha. So that is the thing you should remember. So we have to get the next thing is tan theta minus alpha equal to Ft by Fc. It is a thrust force of cutting force. It's a tan theta minus alpha equal to Ft by Fc. Here also you can remember Ft by Fc. So you can easily remember the formula. Next, we are having some important formulas here. Shear area equal to A sub S equal to Bt by sin pi. So shear strain rate is the ratio of shear velocity to the top shear thickness. Shear velocity to the top shear thickness, and the shear thickness can be calculated by T by sin pi. So here you can easily remember. So we are having this is B into shear thickness. So shear thickness is nothing but T by sin
So you can get here the same formula. It is a shear strain rate is the ratio of velocity of shear velocity to that of shear thickness. So shear strain you can easily get that cot pi plus tan minus alpha or r cos alpha divided by sin square pi, r cos alpha divided by sin square pi. You can remember that tan pi equal to r cos alpha. You can get this tan multiplied r cos alpha divided by 1 minus r sin alpha. No, so this is the tan pi, but here sin square pi will come. R cos alpha divided by sin square pi will come. Okay. Then R is given, you can easily calculate it by using that formula. So we are having velocity relationship. We already solved the velocity relationship previously. So it is Vs by we already solved the velocity relationship of the Merchant circle. So Vs by cos alpha, V by cos pi minus alpha equal to Vc by sin pi. Vc by sin pi. So you should easily remember by these things. So V is the cutting velocity, Vc is for flow velocity. You can find any one of the angle or any one of the velocity by using this formula. So next is we already discussed about the cutting power. Cutting power equal to cutting force into cutting velocity. Here they are using Vc, that is not Vc. So we can say that our notation is Ft into this cutting force, cutting velocity. Cutting torque, simply Fc torque. And material removal rate, we can calculate V into T into Vc. This Vc is nothing but here we are using V into T into V, cutting velocity. So that is the cutting velocity. So this is total energy formula. Already mentioned. Total energy equal to shear energy plus frictional energy. Total energy equal to shear energy plus frictional energy. To calculate the specific energy, it has to divide by the MRR. What do you mean by specific energy? Energy per unit MRR is the specific energy. So now we are going to discuss about merchant analysis and modified merchant analysis. So in merchant analysis we already know that 2 pi plus beta minus alpha equal to pi by 2. In modified merchant analysis what happened? 2 pi plus beta equal to cot inverse k, where k is the machining constant. 2 pi plus beta minus alpha equal to cot inverse k, that is the k is the machining constant. And the Ernst merchant theory. So this is the another form. So same thing, it may be put in the another form. Okay, pi equal to pi by 4, open the bracket, alpha minus beta by 2. Alpha minus beta by 2. So in terms of pi we are speaking, so it has to put it in the that type. So next, slip line feed or Lee and Shaper theory. Lee and Shaper worked on the work material. They have made the assumptions. They made the assumption the work material added of the tool is as ideal as behaves as ideal plastic mass. The tool behave as the work material added of the tool behaves as the ideal plastic mass. There exists a shear plane, so we need shear plane to cut. No hardening take place. These are the three important assumptions. The first thing is work material again of the tool behaves as the ideal plastic mass. The work material again of the tool behaves as the ideal plastic mass. Second thing is there must be shear plane for cutting. The third thing is no hardening of chip take place. So the relation is pi plus beta minus alpha equal to what we will here 2 pi plus beta minus alpha equal to pi by 2. Okay, this is merchant theory. Lee theory is pi plus beta minus alpha equal to pi by 4. Lee and Shaper tells like this. Next, tool wear. We are going to discuss about the tool wear. Tool wear or mechanism of tool wear are 5 things. So So it is abrasion or adhesion, diffusion, fatigue wear or oxidation wear. So we are having 5 things on the tool here. The first one is abrasion, the next one is adhesion, and the diffusion, fatigue wear, oxidation wear. So what do you mean by abrasion? Abrasion is the surface containing odd particle. Because of the odd particle, that sliding, because of the odd particle sliding take place. Sliding may dislodge the material, dislodge some material. Then adhesion, adhesion is because of the high temperature. High temperature, the sliding causes fracture in the fracture of the welded joint material is lost surface. So it has to be the pressure between the chip and tool metallic bonding take place at the contact point. High temperature at the contact point. High temperature at the contact point. This is the adhesion. And diffusion alters in the metallic crystal from the high concentration region to the low concentration. It travels. Diffusion means from high concentration to low concentration. It travels. Atoms in the metallic crystal. Fatigue wear. On the microscopic level, will of the tool be eroded, and the fresh shield will be formed. So yield of the tool is eroded and the fresh shield will be formed in the fatigue wear. This will be formed by the interaction with the workpiece. So tool interact with the workpiece. During the interaction, the fatigue wear take place. Oxidation wear. Oxidation wear caused to the oxide layer. Oxide layer will be removed by the next cut. Okay, so one by one. This abrasion, odd particles. Abrasion occurs with odd particles. Adhesion, high temperature. High temperature. Diffusion, it is moving from one region high concentration to low concentration. Fatigue wear, interaction between tool and workpiece. Interaction between tool and oxidation wear, oxide layer. Okay, so these are the 5 things you should be remembered. So first abrasion, high odd particle, adhesion, high temperature, diffusion, move from high concentration region to low concentration region. This is fatigue, interaction between tool and work. Oxidation, oxide layer will be formed. So these are the some of the wear mechanism. It must be remembered for our lifetime. Next, we are having types of wear. Types of wear are flank wear, crater wear. This flank wear occur on due to the work hardening. Flank wear occur due to the work hardening, and the main reason is abrasion and adhesion. Abrasion and adhesion. The crater wear also called as face wear. It occurs at a short distance. This is the famous question because of the high temperature. Because the crater wear will always from the some certain distance. Because this region the temperature will be maximum. It occurs due to the diffusion. Okay, so abrasion, adhesion, diffusion, fatigue, oxidation. So these two are reason for the flank wear, and this one is the reason for the crater wear. Abrasion and adhesion are the reason for the flank wear. Diffusion is the reason for the crater wear. So it leads to increase in the cutting temperature, weakening of tool, friction cutting force. So those are the points we have to remember for crater wear. So next is tailored tool application. We already discussed V power n equal to constant. This V is the cutting speed, T is the tool life, and C is the machining constant, and N is the tool life exponent. So you can observe the different values of N here. So these are the different values of N. So you have to observe from HSS it is low and carpet somewhat higher, and ceramic that somewhat higher. So for cutting speed and tool life, normally the graph will be hyperbola. For ln of P and ln of T, it is a line. So it is a constant slope. So N equal to this is the log V plus N log T equal to log C. So that is the log graph will be linear, but actual graph is the PT graph. Actual PT graph is hyperbola. actuality graph is hyperbola, logarithmic graph will be linear. So when you take spot the log, so you can get the linear line. So this exponential constant can be calculated by using this formula. N can be calculated log of v1 minus log v2 divided by log v2 minus log v1. So it has to be remembered. So modified Taylor equation, you can see we know that t power n, dt power n equal to constant. Instead of that, we are having two more values, we can discuss that. So you can observe here. So our modified rule life equation. What happened? Depth of cut and feed come under the picture. So you can easily observe v t power n, d power x, f or y. Next, important characteristics of tool material. What are the characteristics that tool material has to possess? It should possess oddness. So the oddness should be more, and the wear resistance should be more. It should possess toughness. And thermal conductivity will be more, thermal expansion will be less, and Young's modulus will be more, coefficient of friction will be less, and ease of fabrication typically stable. So we should remember 4, 6, 7 points first of all. So oddness will be more, wear resistance will be more, and the toughness will be more. What do you mean toughness? Toughness is the ability to absorb the shock load. So when the shock comes, it has the ability to absorb shock load, is the toughness. And thermal conductivity will be more because heat has to be dissipated. Thermal expansion should be less because then only the tool will be stable. And elastic modulus will be more, or Young's modulus will be more. And the coefficient of friction will be less. So you should identify these two variables are less. So you can easily remember coefficient of friction will be less and thermal coefficient of expansion will be less. So whenever the coefficient word comes, it is less. So coefficient of expansion is less and the coefficient of friction is less. So how tool material are evolved? At first the carbon steel has found out, and after that high-speed steel is found out, then stellite is found out, after that cemented carbide is found out, cemented carbide also called as cement, and the ceramic found out, ceramic is the cemented oxide, and diamond. Next cubic boronite, we have to see one by one. So this carbon steel is used for hand drills. You can observe it is used for hand drills, taps, dies, chisels. This HSS contain 1841, and you can observe stellite. Stellite is a non-ferrous cast alloy. Stellite is the non-ferrous cast alloy. You can easily remember by chromium, cobalt, and when you see a crow, you can easily remember the stellite. Cr for chromium, Co for cobalt, W for tungsten. And cemented carbide. Cemented carbide is made by powder metallurgy technique. And the ceramic also made by powder metallurgy technique. Okay. And diamond is the oddest substance among all known material. Good thermal conductivity, low friction coefficient, low thermal expansion. So all the things are, and brittle. So only one disadvantage, it is brittle. It is used for machining odd non-ferrous metal like odd carbide, odd nitride. So next is CBN. CBN is the oddest element of the diamond. CBN is the oddest element of the diamond. So you can see here. And Yukon is the 50% Colombian, 30% titanium, 20% tungsten. So 50, 30, 20. It is produced by rolling. This Yukon is produced by rolling. So these are the important points we should just be remembered for the tool material. So we have high carbon steel, and then high speed steel, stellite, cemented carbide or cement, ceramics or cemented oxide, next is diamond, next cubic boron nitride, next Yukon. This Yukon is produced by rolling method. So effect of parameter on tool life. What are the parameters which affect the tool life? Is we should know that S, F, D, N. Speed, feed, depth of cut, and nose radius. So by increasing the feed and depth of cut, what happened? Tool life decrease. Because it increased the cutting force. Tool life why decrease? So cutting force is increased. Cutting force increase, tool life decrease. So that is the reason we get that size and structure, coarse grain structure, the workpiece has coarse grain, the tool life will decrease. When the two material are fine grain structure, so grain structure, coarse means tool life decrease, fine means increase. So by increasing the increment in cut, because of the increment in cut, tool life decreases. So these are some of the parameters has to be remembered. So first we speak about the cutting speed. Cutting speed, higher the cutting speed, less will be the tool life. So cutting speed increase, tool life decrease. Okay, speed increase, tool life decrease. And similarly we can go for feed and coarse grain and increment cut. So these are the parameters which has to be remembered for the tool life affecting parameters. Next, we should know about the machinability index. What do you mean by machinability index? Machinability index is the cutting speed of the metal for 1 minute tool life with the cutting speed of standard material. So we are having some reference standard material. So our cutting speed is compared with the standard material cutting speed. That ratio is called as machinability index. So we are having machinability index for different materials. You can observe here. For different material, we are having different machinability index. Next is machinability. What do you mean by machinability? The ease of the metal which can be easily machined. So ease with which material can be machined. Given set of cutting condition. So factor affecting machinability are tool life and surface finish. So larger tool life means better machinability, good finish means more machinable material. So both the variables, tool life will be larger and the surface finish will be good. These two are the requirement for the machinability. Next, you have to consider the factors for evaluating the machinability. This tool life and surface finish we already discussed, and some more points you have to add: cutting force and power transformation, and types of chips and shear angle. Those we can add another 4 variables. So first you know that the tool life is the important parameter for machinability, surface finish is the next parameter for the machinability, and the cutting force is the next parameter, cutting power is the next parameter, types of chips and shear angle. So all the 6 variables you can take into the account. Next, economics of machining. In economics of machining you can get the productive cost. This is non-productive cost is the fixed cost, so it will be covered slightly. And tool changing cost and tool grinding cost. Tool changing cost parallel to the tool grinding cost. So tool regrinding cost is the tool regrinding cost. Both are parallel, you can see here. And you can get this is the machining cost. Machining cost, what happened? It continuously machining cost. It is the machining cost. Total cost will come as the U curve. Total cost is the U curve. Which cost will come as U? As a U. So it is a total cost. So machining cost decrease linearly. Tool changing cost increase linearly. Tool regrinding cost increase linearly. So we should know that tool changing cost increase, tool regrinding cost increase, machining cost decrease, total cost U shape. So these are the 4 things you should be remember. And non-productive cost, it is horizontal line. So it is important to draw the economics of machining diagram. It is important to draw the economics of machining diagram, which will be asked in the different exams. There are 3 criteria in economics of machining. So first, minimum cost criteria. Minimum cost criteria, minimum that velocity, optimal velocity can be calculated by C by 1 by n close the bracket. Similarly, we are having 6 different formulas. These formulas can be used for the find out the optimum velocity and the optimum tool life. Among these formulas, this formula is important, and this formula is important. So this is a maximum for maximum profit rate. It will become like this. So you should find out the minimum total cost and maximum production. The line, the deviation between the the velocity in between the minimum total cost to the maximum production rate is called as high efficiency range. So if this zone is the from here to here, it is the high efficiency range. What do you mean by high efficiency range? The range between the minimum cost to the top maximum productivity. Minimum cost to the top maximum productivity. So when you compare the optimum, so at minimum cost will come at the minimum, the maximum production rate will come at the maximum, and in between profit rate will come. So in between profit rate. So production rate velocity will be more, minimum cost velocity will be less. In between those two velocities, profit rate velocity will come. So when we are compare the cutting speed for mild steel single point cutting tool, it is 15 meter per minute, and cast iron is 22 meter per minute. So for cast iron, cutting speed is more compared to the mild steel. Ductile material, the cutting speed is here. You can for single point cutting tool that too. Okay. So for tool material, aluminum, the rake angle is 25 degree. For brass, the cutting speed is 40 meter per minute. For mild steel, we are having 30 meter per minute. When you use the tool material, for different work material, for the corresponding tool material, what are the cutting speed? You have to remember these things. Next is cutting fluid. Why cutting fluid is used? We should know that. Why cutting fluid is used? So what are the properties of cutting fluid? Properties of cutting fluid is thermal conductivity will be more, and viscosity will be less, and specificity will be more. Molecular size, a bracket small molecular size should be there. Surface tension will be more, and chemically stable, non-toxic, non-inflammable. So we should remember K, C, sigma. So these three are, what is K? K is thermal conductivity. What is C? It is specific capacity. Sigma, surface tension. All the values are instead of sigma you can use S also. So KCS is, you can easily remember. KCS should be more. K thermal conductivity, C specific capacity, S surface tension. So all these three variables should be more. What is the thing which should be less? It has low viscosity. So for different work material, we have different cutting fluid. So for steel, we have to use water soluble cutting fluid. For aluminum, it is the mineral oil, soluble oil, or kerosene. Aluminum, and for cast iron, it has to be machined dry. Cast iron has to be machined dry. In fact, no cutting fluid can also be used for cast iron. For brass, it is mineral oil plus 10% fatty oil. So for carbide we are using water as the cutting fluid. For intermittent cutting operation, for the machine like shaper, planer, slaughter, for these machines doing the intermittent cutting operation, what happens? So no cutting fluid is used. So these are some of the things you should make a note.
We discuss all the concepts in the metal cutting for the past 5 days, and now it is a refresh of all the metal cutting principles, and we should know about the different assumptions in the merchant theory and Lee and Shaper theory. So we should know the function of the cutting fluids, and what are the cutting fluids used for specific purpose, for specific material, for specific machines, those things we have learned, and the machinability index and the importance of machinability, why we should know the machinability, and each machinability operations has to be carried out. Based on the machinability only the material can be selected, and the product we are going to make different cutting angles, rake angle, clearance angles, all those things are learned, and those formulas having the merchant circle relations we have to use to solve the problems. So by using those formulas we can get the clear cut of idea of cutting principles, and we should know about the Taylor tool life equation, which is Vt power n equal to constant. So by using all those formulas you are able to solve metal cutting and tool design problems which are come for GATE, IES and ISRO, DRDO, like that. In all the competitive exam it will be useful. So students, practice well and prepare well. All the best for your preparation. Cheers.